Today we're going to talk about planet Earth, and we're going to discuss something that occurs in the Indian Ocean, the massive gravitational anomaly in the Indian Ocean. Why does this gravitational anomaly exist? Well, before we get into that, we need to establish a few things that geophysicists define quite well. You see, if the Earth were a perfectly spherical, flawless sphere with no irregularities whatsoever, it would be quite neat, because gravity on Earth would be the same at all points on the surface. We know that's not the case. In reality, some places have more mass than others. There are regions where the rock has a different density than other areas. Moreover, we know that the Earth is a bit pear-shaped, as some call it. It's somewhat flattened around the poles and more, let's say, bulging near the equator. So, you have these distinct regions, and all of this, the differences in mass, the various types of rocks, leads to what? It leads to variations in gravitational attraction. Therefore, gravitational attraction depends on how this mass is distributed on Earth. Geophysicists do this through measurements, using a tool called a gravimeter, and we also have satellites that perform these measurements. When you take these measurements of gravitational force at every point on Earth and create a global map from them, you get what we call an exaggerated representation. You have this exaggerated representation of those points, and this produces what we call the global GeoID. One of the most famous models of this is known as the Potsdam gravitational potato. I won't go into too much detail here. It's a pretty specialised topic in geophysics, but here's what happens. So you have this geoid, which is essentially a measure of gravity, and when you see that image of Earth, people say, Earth looks like a potato. Remember, that's not the actual shape of our planet. It's just a representation using gravitational force, just to give you an idea. In that representation, we remove everything else, like the atmosphere, and create that representation which we call the Potsdam gravitational potato. For those interested in diving deeper into this, there's a hint, but it's a highly geophysical matter. Well, why is this important? For us, or rather for geophysicists, it shows how mass is distributed on planet Earth. So far it all sounds pretty straightforward, right? Here's what happened. Back in 1948, there was a Dutch geophysical ship named Felix Andries Vening Manes. This ship was conducting geophysical research in 1948, measuring gravity because it towed a gravimeter. While they were measuring gravity, the researchers noticed something quite strange. They observed that the value of gravity, the geoid, in the Indian Ocean, had a remarkably low anomaly. It was a very low value of gravity in that region. This became known as the Indian Ocean Gravity Low, IOGL, which is one of the most prominent gravitational anomalies on our planet. To give you an idea, it covers more than 3 million square kilometres and is centred about 100 to 200 kilometres southwest of the southern tip of India. As a result, the gravitational pull there, combined with the higher gravitational attraction in the surrounding areas, causes the sea level in the Indian Ocean over this gravitational anomaly to be 106 metres below the global average. This is genuinely fascinating. You've probably heard that we measure altitudes on Earth with respect to the average sea level. In the Indian Ocean region, this is highly anomalous, so it needs correction. But here's the question. What could have caused it? What's the origin of this gravitational anomaly in the Indian Ocean? Well, as I mentioned, this was discovered in 1948, and the reason behind it had remained a mystery until now. The mystery has finally been unravelled. A publication in a highly respected geophysical journal called Geophysical Research Letters reveals that researchers have done remarkable work to uncover the secret. In fact, they generated computer models of how the region there formed over the last 140 million years as Earth's tectonic plates moved. Each model used different variables for the convection of molten material within the mantle. You see, tectonic plates move because beneath the Earth's crust there's a mantle with molten rock, and this mantle changes in composition. So researchers tweaked these variables to see what would happen. It's truly fascinating. Through this, they managed to discover what we call a mantle plume. I've talked about these mantle plumes in other videos, or I will, depending on when you're watching this video. I'll provide links to those videos in the cards for you. So these mantle plumes are areas where seismic waves pass at very low velocities. What's happening down there is that researchers are observing hot, low-density material rising from this mantle plume located under Africa, but it's situated beneath the Indian Ocean, creating this gravity low. Essentially, what's occurring is that you have a piece of molten rock, a slab as we call it in geophysics, and this slab is altering the entire composition, changing the mass contrast and causing this gravitational anomaly, this gravitational low. Researchers explained that a significant portion of the cause for the Indian Ocean gravity low was this African mantle plume. The formation of these plumes was likely due to the Tethyan plates deep within the mantle. So, what happened? Over 200 million years ago, there were two supercontinents on Earth, Laurasia and Gondwana, and there was something called the Tethys Ocean. The Tethys Ocean was situated between the two supercontinents. This is more than 200 million years ago. Just to clarify, both Africa and India were part of Gondwana, but what is now India moved northward into the Tethys Ocean, creating the Indian Ocean behind it around 20 million years ago. That's, so to say, the history of planet Earth. It's worth noting that none of those guys, they don't even know this anomaly exists. That's why I didn't want to consider it, as it already causes a lot of conspiracy theories. But let's continue because it's genuinely fascinating. These molten rock plumes, these bubbles, form when pieces of rock that experienced subduction, meaning one tectonic plate went beneath another, which belonged to the ancient Tethys Ocean, sank into the mantle and reached the boundary between the core and the mantle. What did this cause? It melted that plate, and since it had a different composition, it created a bubble, an anomalous region, and this anomalous region ultimately led to the gravitational low. Seems confusing. This is truly fascinating what these researchers managed to uncover. The Indian Ocean gravity low assumed its current form around 20 million years ago, when these plumes, these bubbles, began spreading in the upper mantle. So the plate kept sinking and sinking. That piece of rock kept descending deeper, reaching the boundary between the mantle and the core, where it completely melted. Then, that material began to rise, as if it were bubbling within the mantle. This bubbling of material occurred around 20 million years ago, and this is likely to continue as long as the mantle material flows around this African mantle plume, which will probably take many millions of years once again, until these flows eventually come to a halt. So there you have it, the researchers. And how did they accomplish all of this? They used geophysical measurements, seismic wave measurements passing through these bubbles, knowing the velocity, and they conducted what we call seismic tomography of the Earth. This uses data from earthquakes that occur worldwide, so we can understand how these waves traverse the planet. By studying the path of these waves, they essentially create a tomography of our planet. With this data, researchers can model all of this and comprehend how Earth has been changing, how these plate pieces have been subducting, melting, and how these bubbles have formed. All of this ultimately resulted from the significant difference in materials. Remember that gravity changes with the density of the rock, and the density of the rock is influenced by the type of material. Changing the type of material changes the density. Altering density changes the gravitational force at that point, and changing the gravitational force creates a gravitational anomaly. This is what's present in the Indian Ocean gravity low. In other words, the mystery of the gravitational anomaly on Earth has been unravelled, a truly sensational piece of work by the geophysicists. And this was the video I wanted to share on the channel today, discussing a bit about our planet Earth. It's always good to talk about it. I enjoy it. Quite logical, right? So there you have it. For those who didn't know, now you have the mystery from 1948 being solved. And now you can use it when people come to you with those crazy theories and ask, hey, how do you explain the gravitational anomaly in the Indian Ocean? because this isn't just a guess. It's measured and has been since 1948. And this gravitational anomaly is there. You know how to explain it, right? Agreed. So folks, that was the video. If you liked it, you know the drill. Don't forget the YouTube package. Share, favourite, subscribe to the channel if you haven't already, and leave your comments, whatever you want to know. Until next time.